we're going to distribute these two parentheses. Multiplying the first gives us 6 cosine squared t. The outsides gives us 4 sine t cosine t. The insides, I like to go down a step, gives us 9 sine t cosine t. And the last, 6 sine squared t. So what we can do is we can obviously combine these two like terms, and we can take these two terms and factor a 6 out, and we're left with cosine squared t plus sine squared t. Those two middle terms give us 13 sine t cosine t. And we learned yesterday that these two together sum up to 1, always. Doesn't matter what else is going on, cosine squared t or cosine squared x plus sine squared x or whatever variable you have in there, as long as they're identical, add up to 1. And so altogether, this gives us 6. These two eliminate each other, and we find that that whole expression condenses down to just 6. So when we graph that function on our calculator, we get just a horizontal line at y equals 6. And so what you can do when you're done is compare the graph of this function to the graph of y equals 6, and you should see that they're identical. All right, the next problem, we had a couple like these on the test. I want to look at a new way of approaching them using our Pythagorean identity. So we have cosine theta equals 2/3, and theta is in the 4th quadrant. So what does that tell us about sine theta and tangent theta? What does that tell us about their signs? Going to be negative because sine and tangent are negative in the 4th quadrant. Very good. So we're going to use identities to arrive at our solution rather than constructing a triangle. So the first identity I'm going to use is my Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. Now, I know that cosine theta is 2/3, so cosine squared theta is 2/3 squared, okay? Because this is equal to cosine theta squared, the output of cosine theta squared. So now I just have to solve for sine squared theta. So I'm going to move over here so I can write just a little bit bigger, make it easier for you to see a little bit. So we have so sine squared theta is going to equal 1 minus the square of 2/3, which is 4/9. Okay, so that's just moving this over. So sine squared theta has to equal 5/9. So if we take the square root of both sides, we get that sine theta would equal, and normally when we take the square root of both sides, we throw a plus or minus in the front. I'll address that in just a second. So the square root of a fraction is the square root of the top over the square root of the bottom. Square root of 5 over 3. So, like I said, normally when we take the square root of both sides, we get a plus or minus. we don't have to worry about both of those because that is parsed by the fact that we are in the fourth quadrant. Since we're in the fourth quadrant, we use the negative value and use negative radical 5 over 9. So if you, sorry, not 9, this should be 3. Wrote it correctly down at the bottom. So if you approach this with the triangle method that we were doing last chapter, you'd still arrive at the same answer. This is an algebraic approach. We did a geometric approach before. You decide which one works best for you. For years, I used the geometric approach. Then I discovered the algebraic approach, found it was faster for me, but it's up to you. So once we've found sine, we can use sine and cosine to find tangent. Because tangent equals sine theta over cosine theta. And we said that sine theta is negative radical 5 over 3. Cosine theta is 2/3. So now you just have to remember your fraction rules. When you're dividing two fractions, you flip the second one and multiply. So we're doing negative radical 5 over 3 times 3 over 2. The 3's cross cancel, and we have negative radical 5 over 2. So the trap there is to forget to mess with your signs. So you have to remember that is why your domain for theta is there. It's to determine whether they're positive or negative. I give you a lot of credit for just finding the values, but to get full credit, you got to then determine whether they should be positive or negative. So like I said, you could have found that geometrically, you could have found that with the triangle, but use whichever approach works best for you. Whichever one you can most get the right answer with most consistently. Any questions on that method for that problem? Okay. The next one is a little bit strange. So we have two different trig functions in this equation, a sine theta and a cosine theta. That's bad. We like to have only one trig function whenever we can help it. A lot of students fall into the trap of saying, oh, well, cosine equals 1 minus sine. It doesn't. Cosine squared equals 1 minus sine squared. So don't make that mistake when the sine and cosine aren't squared. Or some students will look at it and go, well, I could square both sides, and then both sides are squared. Then I've got a sine squared and a cosine squared, and I could replace it that way. That is a valid approach. You can square both sides. It's not the approach I'm going to use, but it works under certain conditions. So you could square both sides if you make sure that you square the coefficient and the trig function. And then you could replace either sine squared with 1 minus cosine squared or cosine squared with 1 minus sine squared. You could go either way with that. So for instance, something like this. And then you get all the sine squareds together and you solve and you take the square root. The problem with this method is that when you square both sides of an equation, we saw this earlier in the book, you tend to create solutions that aren't real solutions. You tend to create what are called extraneous solutions. They work for the squared equation, but they don't work for the original equation. So if that's the method you're going to take, you have to then go back and check each of your solutions and make sure that they actually fit your original equation. So for that reason, I don't use that method. I save myself the work and approach it a little differently. what we can do is we can divide both sides by cosine theta and by 3. So on the left, the 3's will cancel out, and sine theta divided by cosine theta is tangent theta. And then we have on the right radical 3 over 3. Now, you do have to analyze this for a second and make sure, okay, I can do that as long as I'm not dividing by 0. So when would I be dividing by 0? I would be dividing by 0 if cosine theta equaled 0. And cosine theta equals 0 when theta equals pi over 2 or 3 pi over 2. Now, this is a kind of an in-depth approach. The book really doesn't, and the Wiley Plus system really don't throw these kind of problems at you. They don't look at it. They don't make problems where this would be an issue. But it's something to consider in the future when you're solving an equation. Are you allowed to divide by what you're dividing by? Okay. So the question is our equation here ever going to give us a solution where that happens? Are we going to have pi over 2 as a solution? But we know that it can't be, okay? Because at pi over 2, 3 pi over 2, 5 pi over 2, all of those odd multiples of pi over 2, tan theta would be undefined. It would not equal radical 3 over 3. For those values of theta, tan theta is undefined. And so we're not going to get any solutions from that where tan theta is going to be radical 3 over 3 instead. It can't be both radical 3 over 3 and undefined. So we won't have any crossover there. So then it comes down to finding the actual solutions. Now, it might be hard to figure out where that is in this form, but it might be a little easier if we remember that radical 3 over 3 is what we get when we rationalize 1 over radical 3. And when we see the 1 in the radical 3, that should help us tie back to our special triangles. So which angle, you can give it in degrees if you can't remember in radians, which angle has a tangent that's equal to 1 over radical 3? Pi over 6, or 30 degrees. So tan theta, sorry, I ran out of writing there. Let's try this again. So if we got tan theta equals 1 over radical 3, we know that that happens when theta equals pi over 6. That's our reference angle. But notice that our domain is all 4 quadrants. We know that tan is positive in the first and third quadrants, so we want pi over 6 here and pi over 6 here. So our first quadrant angle is pi over 6. What would be the measure of our third quadrant angle? So this part here is pi over 6.
7 pi over 6.
Yep. When we add that half a rotation there, we got to do pi plus pi over 6, which, thank you, Garrett, gives us 7 pi over 6. There's our two solutions. Now, the beauty of these is you can go back and check them very easily. Plug them into your calculator. Does 3 sine of pi over 6 equal radical 3 cosine pi over 6? Okay, and does 3 sine of 7 pi over 6 equal radical 3 times cosine 7 pi over 6? Okay, plug each side into your calculator and make sure you get identical values. Or graph both sides of the equation. Graph y equals 3 sine theta and y equals radical 3 cosine theta, and find where they intersect. Okay. The only problem is when you calculate their intersection on your calculator, it's going to give you the decimal approximation. So then you got to compare that to pi over 6 and 7 pi over 6 and make sure that it's equal. Any questions on that one? All right, the next example is something that's completely different than what we've done so far, I think. So here we have the 2 sine squared t, and we have a cosine t. As I said before, we want only one trig function. You could try to find a way to replace cosine t. Bless you. But that's going to be a pain. So the easiest thing to do is replace sine squared t with 1 minus cosine squared t. Take your time when you do this. I see so many silly mistakes that shouldn't be made at this level because you write something like this when you're replacing that sine squared t. What's the problem with what I just wrote? Yeah, that 2 needs to be distributed over both pieces. So I should be writing it like this. Okay? If you can write it like this and remember to distribute, that's good, but it's poor notation. Technically, reading this, you shouldn't distribute. You should just do 2 times 1. The correct way to write it would be like this and distribute that 2 through. So many students fail to multiply the 2 by both pieces, and then your solution is off. In some cases, like in this type of equation, it could make it pretty much impossible to solve if you don't do that correctly. So we should distribute that out. And now we've got a really strange looking equation. But at the same time, this is one that we actually know how to solve. So the first step I'm going to do is move everything to one side. It doesn't matter which side you move it to. I like to move it in such a fashion that the squared term or the highest power term is positive. So I'm going to move everything to the right and just kind of rearrange a little bit. So I'll have 0 equals 2 cosine squared t minus 3 cosine t plus 1. So the negative 2 cosine squared t obviously moved over. The 2 was subtracted from the 3 and then moved to the end. Now, this is something you might see quite often. what might help is to look at this a little bit differently. We could look at this as if it were 2x squared minus 3x plus 1. So basically what I just did is I replaced cosine t with x. What methods do we have to solve this equation? We could factor, okay, and if we're having a hard time factoring, what's our second method? Quadratic formula. So if you can't factor it, or if it's not factorable, you can use the quadratic formula. If you can't factor, you're having a hard time using the quadratic formula, you can graph it on your calculator and find the x-intercepts. All of those methods are available to you. This one is factorable. So just as a reminder from the first couple chapters, we're looking for the product of 2 and 1, which is 2. We're looking for factors of positive 2 that add up to negative 3. And so the factors of positive 2, which again came from the product of 2 and 1, that add up to negative 3 are negative 2 and negative 1. Now, you might have done a shorter version of this in your Algebra 2 class or your Algebra 1 class. This is what's actually going on behind the scenes. If you're doing a shortcut, this is what's going on behind that. We use factoring by grouping. The first two terms have a 2x in common, and we're left with x minus 1. The second two terms, since we want an x minus 1 to match this x minus 1, we need to factor out a negative 1. And so our final factorization, both terms have an x minus 1. When we take that out, we're left with 2x minus 1. Then our zero product property tells us that this equation has solutions if x minus 1 equals 0 or 2x minus 1 equals 0. So we have solutions when x equals 1 or x equals 1/2. But we said that x is really just a replacement for cosine t. So we're looking for when cosine t equals 1 and cosine t equals 1/2. So if you don't want to replace the cosine t with an x, you don't have to. I just did it just so it looked more familiar. If you were doing the quadratic formula that way, instead of having x equals negative b plus or minus all that, you'd have cosine t equals negative b plus or minus all that stuff from the quadratic formula. Does everybody understand how I got all the way to here? Are there any questions on how we're not done, but are there any questions on how I got to here? I'm sorry. You misunderstood me. This is not a step per se. This is not an alteration of that equation. It's just that's just a reference point. Okay, this is a change of my Pythagorean identity. So it's not a step going from 2 sine squared to sine squared. It's just I was just writing down what identity I'm using and plugging in here. Does that make sense? Okay. That's a good question. Sometimes I write those things in there and I don't stop to think of what they look like. Any other questions? Okay, so once we've gotten to here, it's just a simple matter of identifying what angles in our domain equal 1/2 and 1. For cosine, of course, this should be a t, not a theta, or the t should be thetas one way or the other, but that's just a typo. So between 0 and pi, where does cosine equal 1? Remembering that cosine is the x-coordinate on our unit circle, where is it equal to 1? Zero. It sounds like, maybe it's just my ears. It sounds like people are whispering it, but afraid to say it too loud. Or they're just too quiet. So at 0 radians, or 0 degrees, either way, cosine is 1. Where is it 1/2? Pi over 3, or 60 degrees. We don't have, this domain extends into the second quadrant at 0 to pi, but cosine's not positive in the second quadrant, so we don't have any extra solutions over there. These are our only two.